Welcome to our discussion on exponential equations. We'll start off with some brief just definitions, right? Large and small numbers are often represented in exponential form in scientific notation. Growth and decay usually happen in exponential formulas. Scales like the decibels are logarithms. Richter scales for earthquakes are logarithms, right? So these types of things are used quite a bit in science and nature, so it's a good idea to have at least a basic understanding of how they work. So a basic exponential equation is anything of the form b to the x equals n, where b is the base, x is the power, and then n is some number. Some simple examples, right? If we tried to solve 2 to the x equals 14 by just plugging in values for x, we can see that once we get to 2 cubed, we have 8, which is still too small, but 2 to the 4th is 16, which is too big, and we know the answer for x is somewhere between 3 and 4. But how do we find that exact value? And you can't do that without being able to take logarithms, right? So what is a logarithm? Well, a logarithm is basically just the mathematical operation that undoes an exponential, right? So we always, in math, there's always two sides to the story, right? For addition, we then have subtraction, which undoes it, right? And vice versa. And then you can multiply, but you can divide, which undoes that, right? You can square something, but you can take a square root, right? So there's always these things that does the other operation. So you can have an exponential function, which raises something to a power, but then you can have a logarithmic function, which kind of undoes that and solves for the variable you're trying to solve for. So when you see 2 to the x equals 14, you have to realize that the unknown, the thing that we don't know, the x value, is the exponent of the base 2. So it's basically saying what power of 2 do we have to raise, what power do we have to raise to 2, right, to get 14. So x is that power of 2 that gives us 14. So we can think of x as being this exponential power where 2 is the base, right? So that's why 2 is down below, and 14 is the answer. So we can just kind of come up with, rather than using exp to denote this exponential base, we'll say that x is log base 2 of 14. Now that seems like some magic that we just kind of replaced one for the other. But basically all that's happening with a log is we're restating an exponential. It's kind of like the jeopardy of math questions, right? We have b to the x equals a. Well, now we're saying x equals log base b of a. It's still asking the same question, right? B to the x equals a. If you don't know the x, you're still asking the question, what power do we have to raise b to in order to get the answer of a? Well, that's exactly what the log is saying. It's saying x equals log base b of a, which is a fancy way of saying we're looking for a power, right? B is my base. We're looking for a power of b that gets me a. And the log function is just the function that does that in a direct manner. You can see that this isn't directly solved for x, right? X is stuck here. We haven't isolated x. So all the logarithm does is it restates this formula, right? Restates this equation with x all by itself. So when you see logs, just remember that logarithms, right, regardless of what the base is, log base 2, log base 5, log base e, which is natural log, log base 10, which is the common log, doesn't matter what it is, all those logs are really just exponential equations in disguise. So when we see 5 squared equals 25, that's easy, right? We know that. A 1/8 is 2 to the negative 3, right? These things are all correct. We know these equations. There aren't any x's in here. But we can rewrite them in terms of log equations to see how it works. And kind of a nice little visual that helps students see that is if you do a little counterclockwise circle, right? So you start at the base, right? Because we always start at the base. You wrap around here, and then you keep wrapping till you get to here, right? And that says 5 raised to the power of 2 equals 25, right? That's all it is. It's rewriting that equation. So it solves for the exponent. Same thing here. We can rewrite it around, right? 2 to the negative third equals 1/8. 64 to the 1/2 power equals 8. Now, as I mentioned before, base 10 is called the common log because that comes up a lot in various things, like decibels and the Richter scale and things like that. But there's also a lot of things in nature that are base E. And we've also, if you've seen my videos on finance, they also come up in money. Those are called natural logs. And we write it as lnx, pronounced like that, lnx. And that comes from, it's the French pronunciation, which is logarithmic naturel, right? So that's where ln comes from. It just means the natural log. So we've got log of x, which means base 10, natural log, or ln of x, which just means log base e. So all these they're two of our special bases that come up so much that we gave them their own special names, so we didn't have to keep writing log base e and log base 10, right? This is a lot more complicated to print in typesetting than this is, right? So way back before computers, and they had to kind of write up math books with the old-fashioned typesetting, subscripts and postscripts were really difficult. So instead of doing this over and over again, which is difficult, we gave it a different name, which is much easier to print. And same thing with this. Instead of doing this over and over again, which is difficult to do, we gave it an easier shortcut to print. Okay, so how do we evaluate these things? Well, if you've got a calculator, it's really easy. You just slap it into the calculator and you're done. So to evaluate any log of base 10 or base e, most all calculators will have those buttons, and you can do them. If you have a log that's not of base 10 or base e, you have to use the change of base theorem to change it into one of those bases so that you can evaluate it in your calculator. And it's really simple. It's just whatever the base is, that becomes the number on the bottom log, and whatever the number is, that becomes the number on the top log, right? So you can see that log base 2 of 8 becomes log of 8 over log of 2, or natural log of 8 over natural log of 2, and both of those work. If you did them in the calculator separately, you would see that you would get the same answer. Now we know log base 2 of 8 has to equal 3, because remember it's saying 2 to what power equals 8? Well, 2 cubed equals 8. And if you calculated each of these individually, you'd get these really ugly decimals, and then if you divided them, you would get something close to 3. But if you did it all together at the same time without, like writing one out and re-putting it back in the calculator, you would get exactly 3. And that's the difference between rounding and not rounding. Okay, so either way works. Logs and natural logs, doesn't matter which, just choose whichever one you like. I tend to go with natural log just because, they're quicker and easier to write. So here's the basic change of base formula. If you want to know where it comes from and how it works, it's a pretty basic proof. I'm not going to bore you with it here, but the bottom line is it's all based on powers, right? And it's really easy to remember because whatever the base is here, that becomes the number here. Whatever the number is here, that becomes the number there. And then the new base is whatever you want it to be. Obviously, you're not going to change it to anything other than base E, which is natural log, or base 10. So now we can do these. We can turn that into log 3 over log 7, stick that in the calculator, and get basically 0.56. We can do the other one. We can turn that into log of 3.84 over log of 3, or remember we could have been doing these natural log of 3.84 over natural log of 3, and get 1.22. So now we can return to the idea of solving these things. How do we find this answer? Remember we figured out that 2 to the x equals 14 was somewhere between 3 and 4. Well, we can find that exactly by knowing that it's log base 2 of 14, and we can figure out log base 2 of 14 by using the change of base formula, right? Because we can't calculate log base 2 in our calculators, but we can do log of 14 over log of 2, and we get basically 3.81, which was right where we thought it was going to be, somewhere between 3 and 4. Okay, so solving exponential equations really comes down to some simple things. The common log, right, base 10, natural log, base e, and then arbitrary, all the other ones are just other things, right? This is base 8. And it really doesn't matter what the base is. You solve them the same way. Now, if you have log base 10 and log base e, you obviously want to use logs and natural logs for those too. And if you have log base 8, you can think along the lines of, well, I'm just going to do log base 8 of that and then do change of base. But there's actually kind of a quicker way of thinking about these. If you know anything about the rules of logarithms, there's one rule you need to know. And this works for all logs, right? So log of any base of x to the a, let's say, equals a log of x, right? And again, it doesn't matter what the base is. So what this means, if you take a log of an exponential, right, something raised to a power, it becomes the power times that log. And once you know that, it makes solving all of these really easily, because if I want to solve this, all I have to do is, let's say, take natural log of both sides. Because then I get natural log of 10 to the x equals natural log of 5. Now, obviously, since this is base 10, it'd be easier to do log rather than natural log. But I'm going to show you that it works for anything. Because now the x comes down in front, right? And we have x natural log of 10 equals natural log of 5. And so x is going to equal natural log of 5 over natural log of 10. And if you plug that into your calculator, you would get the same answer as if you just took log of both sides. Well, the reason, obviously log would work better for this, natural log would work better for this, but where we want to use this trick is when we have any base other than e and 10, right? Because with 10 and e, we can just do logs and natural logs, and the e's and the 10s just go away. But for this one, it's not going to work. So let me show you what I mean, and then we'll go back to this concept with part C. All right, so with 10 to the x, it's going to be a lot easier to just use it as log, because we know this is saying log base 10, right, of 5 equals x, and we get, there's our answer. One fell swoop, nice and easy. Same thing with e. You're basically taking the natural log to solve for it, and get natural log of 3 point blobbity 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 equals that negative 0.06, right? Divide both sides by the negative 0.06, and you get negative 20, whatever, right? Okay, so now here's what we're thinking this one is, right? So we know, okay, to solve for x, we got to take log base 8 of both sides to undo the 8. But how do we calculate log base 8? Well, we have to change a base, right? Log of 156.8 over log of 8. But really, that just comes from taking log of both sides. So if you take log of 8 to the x equals log of 156.8, right? Remember our rule, the x comes down in front, so we have x log of 8 equals log of 156.8. And then, of course, you divide by log of 8 to get rid of this, and you see how this is the same thing as that. So that little rule of remembering the powers, right, when you take log of something to a power, the power comes down in front, can help you solve all logarithmic functions, or all logarithmic, equations and all exponential equations, regardless of what the base is. Okay, so here is a much cleaner printout of what I'm telling you. And you see you get the same exact answer. All right, so that's the big thing, right? Is that either you can, think of it as taking log, base 8 of both sides, or you can just do log of both sides with some simple algebra, and you basically get the exact same thing. All right, that's everything we need to know for exponential equations.